question asked to make sure what is S here. I will rewrite the definition here but I will re-explain this in the course of the coming lecture. S is minus integral, or S of mu is minus integral rho log rho d nu, where rho is the density of mu with respect to nu, the measure. So we shall explain about this functional. Well, let's do it right now. So in this second lecture, I will take the various theories which I mentioned and develop a little bit more each of these theories so that we can understand where the connection stands. And in the third lecture, I will go more in the details of the synthetic theory and what one can prove. So remember, there were 4 theories. I said there is curvature, optimal transport, entropy, and gradient flow. So we'll take them all 4 in turn and start with the entropy. So this is the entropy. What is the meaning of entropy? I will remind you that entropy was introduced in the 19th century, first as a way to measure the irreversibility of certain processes in thermodynamics. And the big names associated with entropy there were people like Carnot and Clausius. And there are certain formulas we learn in thermodynamics, variation of entropy, something like a heat exchange divided by temperature. But this is part of the macroscopic interpretation of entropy. What was discovered by Boltzmann is that there is also a statistical interpretation of entropy, which can even be stated in kinds of combinatorial terms. So Boltzmann says the following. If you have a certain system that you are examining, and a part of the system is unknown to you and a part is known, you look at all the unknown and you take the volume and the logarithm of the volume of the unknown. And this you call the entropy. So it's a measure of how you are lacking knowledge in a certain configuration. So let's explain this directly on some example. Suppose that you have various states, 1, 2, 3, 4, 5. Maybe these are energy levels for some atoms, maybe it's some kind of population and so on. These are various states possible of a certain microscopic system. And you know that certain individuals or certain particles are of type 1, certain are of type 2, others are of type 3, and so on. And you also know that you have no way to distinguish between particles except through this state. For instance, you are able to measure the energy of an atom, but nothing else. And so you know that a certain fraction has energy level 1, a certain fraction has energy level 2, etc. And all you can know is the fraction. And you ask then about the microscopic states of a given particle. And you ask how many ways are there to distribute capital N particles among k different states such that for each state J, the number of particles in state J divided by the total number of particles is equal to a certain Fj, which is the observed frequency, which is the expected frequency. The result depends on capital N and depends on the frequencies. And it's a combinatorial exercise. And the answer is W equals n factorial divided by nf1 factorial, etc., nfk factorial. If the fj's are rational. And n, capital N, is such that all the nfj's are integers. So this is a solution of this problem, and this we consider as the uncertainty, is the number of possible configuration. Let's call it the microscopic uncertainty. It tells you about all the possible microscopic ways that you can prepare your system so that it matches the macroscopic observation. And now, think of capital N as a number of atoms, for instance, or something like this. You want this maybe a huge number. So what you do to make sense is to take the logarithm and divide by n and take the limit as n goes to infinity. And what you will observe is that the limit is up to a constant minus sum of fj log fj plus constant. So j going from 1 to k. So this gives the explanation for the Boltzmann formula. This is the Boltzmann entropy. You see that it's about counting possibilities. It's actually like a combinatorics problem or like a statistics problem. There is another way, yes?
Why do you take one off? I mean, why not any other function? I don't understand.
You saw one first answer would be that if I know the result in the end, I see that log is the only possibility, because if I had to, say, a power or divide by something, I would have been impossible to get a result there. But there is a more profound answer about the logarithm. We may think of this quantity in the end as the typical amount of information which is in one particle. You see here, if I take this, say, consider this as information, when I divide by capital N, it's like the mean information for each particle. So it says this is the amount of information that I get when I take one particle and measure its state. And then this doesn't answer the log, but in a moment you will see why it answers. To continue the analogy, suppose that all particles are in the same state. And I measure, I see all particles are in state number 1. So if I take a particle and I measure what state it is, I will find 1 and I gain no information. 0, not interesting. If on the other hand it's very spread, I take one particle, there is some uncertainty, I measure it and I gain some information. And this information will be big, typically big. So this is the mean information that I get when I do the measurement. Now, it's the same interpretation that you have in the theory of communication. Shannon, in the 40s, made this theory. Let's model the way we communicate as a kind of random process. And whenever we decipher a unit of language, maybe a letter, maybe a word, depending on your modeling, we gain some information by learning something about something which was unknown before. Let's call it the information per character. And if I listen to two sources of information which are independent, if I think of it as random processes, it will be multiplying the probabilities, because independence comes with multiplying probabilities, tensor product. But as I think in terms of information, I want to think of it like this information adds to this information. Now, in the theory of Shannon also, what makes the value of a character is the fact that it is rare. Rare probability means a lot of information. But it should depend on the probability of that signal. So, independent signals mean multiplying the probabilities, but adding the informations. To go from the multiplication to the addition, the only possibility is the logarithm. And that's the information theoretical explanation for this logarithm. It will change the multiplicative probabilities into an additive information. So let me rewrite this statement in a slightly different way. It is not obvious that it is the same, but if you go really inside it, it becomes the same. And you will see also that I state it in a more general way. And it's called the Sanoff theorem of large deviations. It's still part of this information about entropy. It's a modern way, mathematical way, to think of the Boltzmann equation in a way which is very general. So take x1, x2, etc., xn, independent, identically distributed random variables. Okay? And let's assume that their law is equal to mu. And is it okay? It's to give us energy. So let's call it nu. It will be more consistent with notation I will use later. So this is a probability measure. And if I have these random variables, I can write the empirical distribution, mu hat, 1 over n, sum of delta xi's, I going from 1 to n. So it's like these are the observations, and I take the sum, the combination of the Dirac masses. And then this has to be approximately nu as n goes to infinity. This is like the law of large numbers, but in the sense of probability measures. And people in statistics sometimes call this the fundamental theorem of statistics, meaning that from the observations of identically distributed random variables, you can reconstruct the whole of the law as n becomes large. And this is almost surely. But now you ask, which is the typical mistake that I can make? Maybe I am listening to these random variables, and they show me some suggestion for some law, but maybe the wrong one. So what is the probability that mu hat is approximately equal to something mu, which is not the true value nu? And the answer is that this is approximately, in some sense, exponential minus n times something which I will write I nu of mu. So it's exponentially small, and this quantity, which is always non-negative, I nu of mu, is just the negative of the entropy. So it tells me if the entropy is very high, so the information is very low, so the coefficient here will be small. And so it means maybe the error is not so small. Maybe the probability is not so small, and maybe I will make mistakes. So high entropy means it's rather difficult to evaluate the limit. If the entropy, on the other hand, is very low, then the information is very high. The coefficient here is large, and so this is a very small quantity. And so the probability that I make a mistake is very, very small. So a low entropy means a distribution which is easy to observe, and a high entropy distribution which is less easy to observe. High entropy corresponds to difficult to observe, in some sense. So this is about the entropy. Let us say that entropy is a very versatile tool which has been introduced in statistical physics, rediscovered in communication theory, but also plays a role in, for instance, partial differential equations. Entropy was used in the famous theorem of John Nash about the regularity of diffusive equations, one of the most famous papers in the theory of partial differential equations in the 20th century. But entropy was also used by Grigori Perelman in his proof of the Poincaré conjecture, which is maybe the most famous paper of 21st century so far in mathematics. So entropy is very useful. Is very useful in PDEs, and I gave just these two examples, Nash and Perelman. So statistical physics, probability. Let me mention that, for instance, one may prove quantitative versions of the central limit theorem, with entropy. Classical proof, the most famous proof of central limit theorem is by Fourier transform, and that's the proof we learn in early courses in probability theory. But you can also do it with entropy. It's a much more difficult proof, but much more deep, with meaning. Because with the Fourier transform, Gaussian appears in a kind of strange way, because Fourier transform of a Gaussian is a Gaussian, but this has not much meaning. While in this context, entropy appears because Gaussian is a distribution with maximal entropy when you fix the covariance. And so this comes with a very clear statistical meaning. So this is with all we shall say about entropy. And more generally, entropy, so the things is that Gaussian distribution maximizes entropy for fixed covariance. And in general, more spreading means more entropy. It is in line with this. If you have a distribution which is very concentrated, it will be easy to find which is the values of the random variables, easy to find the distribution. If it is very spread, it will be much less easy. In kinetic theory, we learned that entropy goes on and on for a gas which is enclosed in a box. But also we learned that the gas wants to invade the whole box. It shows that the spreading goes with the entropy. So good for the entropy. Next, let us say more about gradient flows. So take a function u from some manifold to R. Then there is a gradient. There is a differential and there is a gradient. du is the differential and grad u is the gradient. So that grad u scalar product, the tangent vector psi, is the same as du applied to psi. And as I said, the gradient flow of u is the flow dx dt equals minus grad u of x. Gradient flows, you can find them everywhere. Many equations are, in fact, gradient flows, and they will make a certain energy go down and down. For example, the heat equation du dt equals Laplace u is the gradient flow of the functional capital U. Okay, let's not write it with u here. Let's put here phi. Of u of phi is equal to integral grad phi square in L2. When you compute the gradient flow of this in L2, you find the heat equation. So it's a way to make this Dirichlet energy decrease as fast as possible in the L2 sense. In this example, the space on which this is defined is L2, which is not a Riemannian manifold, of course, but still is a Hilbert space, so that you have quite some regularity. But later it was found that you can do gradient flows in metric spaces which are not even Hilbert. There are several theories to do it. Here is a way to define gradient flow in a metric space. Let's say y delta, yd. This is my metric space, and this is a distance. Discretize the problem and choose a time step, a small time step delta t, let's say, a small number, and compute x1, x2, etc., xn, etc., as follows. X k plus 1 minimizes u of x plus distance xkx square divided by 2 delta t. So at each time step, you minimize a combination of u and the square distance to the previous approximation. And this gives you a certain curve. This is time 0, delta t, 2 delta t, 3 delta t, etc. And so you have a certain x0, x1, x2, x3, etc. I write it like it's a graph, but of course, it may take values in some infinite dimensional space or whatever. Yes?
When we observe the integration below, we see that in any small point, all the configuration space is perturbed by the flow. I mean, in any small point, all the configuration space receive kind of perturbation. I think it doesn't have any statistical mechanical integration. It seems to be wrong.
The perturbation, indeed, you may say in any small time, there may be some complete change of the solution. That is not the case because here, delta t is very small. So if you make a big variation between xk and xk plus 1, if you make a big variation, this term will be very large. And it has no way that this can be a minimum. So if you want it to be a minimum, this term and the fact that delta t is very small will impose that the next is very close to the previous one. The fact that there is this weight here with a very small denominator prevents it from going very far, so that it will be an almost continuous solution. And actually, indeed, when you make delta t go to 0, you obtain in the end some continuous flow, continuous curve. And as delta t goes to 0, you recover this approximation. For instance, you can write it as an exercise, this to be very clear. If you start for the heat equation with a certain function phi 0 in L2, and then you look at phi as phi 1 is the minimizer of integral grad phi square. Okay, we should put a 1/2 here. Grad phi square divided by 2 plus phi minus phi 0 L2 square divided by 2 delta t, and then you continue. In this way, you will obtain a discrete sequence of functions, which when you let delta t go to 0 will converge to a solution of the heat equation, and so on. But the advantage of this is that you can do it in a very general setting, which is not even necessarily Hilbert space like this L2. Okay? So, let's continue. And now to the big thing, which is the optimal transport. Okay. So, recall the definition in the Kantorovich formulation. Minimum integral c of xy pi of dx dy, where pi is a probability measure which should have marginals mu and nu. Which cost to choose? Original cost function was x minus y in R3, in R2 or R3. But also x minus y squared is interesting in Rn. Also, distance xy or distance xy squared are interesting, and many others. But these two ones are the most interesting in general. That's fact of experience. Let us see what we can say about the best case, maybe, which is this one. You know, square in this case, so it's a Euclidean distance, and it has good properties when you put the exponent 2, just like when you do Lebesgue integration, L2 is the best, the one that has most structure. So let us see, for instance, c of xy equals, let's put just one bar, x minus y squared in Rn. Theorem. A theorem that I shall explain. Theorem is due to Brenier around 1987 something, and other people also worked on this. If mu has a density with respect to Lebesgue measure on Rn, and nu is an arbitrary probability measure on Rn, then there is a unique optimal transport map from mu to nu with cost x minus y squared. And it is characterized by the following property. There exists a convex function, capital phi, such that T is a gradient of capital phi. So here you see a geometric characterization of this optimal transport map, the gradient of a convex function. Remark, if I look at T of x minus T of y, scalar product x minus y, then it is the same as grad phi of x minus grad phi of y, scalar product x minus y. And from general properties of convex functions, we know that this is always non-negative. which means that the transport map is monotone in some sense. It's the definition of a monotone operator. Let me give you an idea of how one can prove this theorem. So, okay, now first remark this, and second, this theorem makes it possible to check that something is optimal. You just have to see if it is a gradient of a convex function or not. First test will be monotonicity, but then if it is gradient of a convex function, you know that it is the optimal. And a third remark, this was part of a revival of optimal transport, which occurred in the 80s. In which 3 different people found independently that optimal transport was useful for their fields of research. One was Brenier in France, discovering that it was good for fluid mechanics, and in particular, incompressible Euler equation. So for non-viscous incompressible fluids, and he found that by using optimal transport, he could construct some generalized solutions to the equations of incompressible Euler system. The other was John Mather in the United States, and he found that using optimal transport allowed him to construct certain so-called invariant measures for dynamical systems. And the third one was Mike Cullen in England, who discovered that it was useful in meteorology, in the study of certain equations from meteorology called the semi-geostrophic equations. So in the 80s, these 3 people independently discovered that optimal transport was important for them, and this led to a whole movement about optimal transport. And this theorem was part of this revival, because it showed that you could have interesting information. At the first time, it was an analytic solution of a tricky non-convex optimization problem, and it was making a link to geometry, because here you have a strong geometric information about convexity. So how do we prove these kind of things? Let's go quickly through the proof, sketch of proof. First, the Kantorovich duality. Which is general and says that minimum of double integral c of xy pi of dx dy is equal to the supremum of integral phi d nu minus integral psi d mu over all functions psi and phi, such that, this is phi psi, such that for any x and any y, phi of y minus psi of x is bounded above by c of xy. And this is for pi having marginals mu and nu. Let me give you in words the economical interpretation of this statement. And we'll assume we are in the world of economics. So here I am overseeing transport of material from initial configuration mu to final configuration mu. Imagine that you are in charge of a bunch of taxis, for instance, and there are a bunch of parking lots, maybe 100 taxis, 100 parking lots, and at the end of the day, when everything is finished, each taxi, each car should go to some parking lot, but you want to match them in such a way that you don't lose too much energy, so this one goes here, this one goes there, etc. And so you want to find the minimal configuration such that initially the distribution is as they are in the city and finally they are in the parking lots. It can be also restated in terms of you are extracting something from a mine and taking it to some place where it will be bought by consumers, whatever. And then arrives some guy who says, let me handle the transport. You will sell me the material at starting point, and I will sell it back to you at the final point. So all we shall agree on is buying price and selling price. Phi and psi. And these will be like two prices. And the guy tells you, I am not a crook. I will never overcharge. So for any starting point and any final point, you can check that the difference in the prices will never be more than the transport cost, so that you will trust him. And then this is like the total amount of money that he will get. So the theorem, and that's why the Kantorovich theorems looked so capitalistic, says that if you want to do it in an optimized way with respect to transport, overseeing everything, it's like you have this intermediate guy who will try to make the maximum profit, and the two solutions will coincide, and it will correspond to a rational choice of the prices. It's a general duality which you can prove as a particular case of the duality occurring in linear programming, as it is said. Anyway, we apply it here, and we find that the solution here will be supremum of what? Integral phi d nu minus integral psi d mu, such that for any x, any y, phi of y minus psi of x is bounded above by x minus y square. What to do with this? We'd like to work on this condition, but it's not something which is very pleasant. But now, rewrite the condition phi of y minus psi of x bounded above by x squared plus y squared minus 2x scalar product y. Okay? Divide everything by 2, and it will be phi of y minus y squared divided by 2 plus minus psi of x, or yes, let's put a minus here, psi of x plus x squared divided by 2 bounded above by minus x scalar product y. And maybe I will change all the signs. And here we are. Okay, now this does ring a bell, and we all know it's like the Young inequality in convexity. X scalar product y bounded above by a function of y and a function of x. So we understand now that we can restate everything in terms of the convexity duality, in terms of the Legendre duality. I remind you that Lagrange duality is star operation such that x dot y is always bounded by phi of x plus phi star of y. And the definition is phi star of y is equal to the supremum of x scalar product y minus phi of x, supremum over x. And so we can change function, taking this as a new function, replacing this by the supremum, and so on, and we arrive at a new problem which is supremum over phi of integral phi d mu plus integral phi star d mu. And equal to infimum of integral x scalar product y pi of dx dy. This is after I expand the square also here in the cos function. Now, if there is equality, it means that integral of phi of x plus phi star of y minus x scalar product y pi of dx dy equals 0. Here, when I integrate phi of x against pi, is the same as if I integrate it over mu, because pi has the marginal mu. And so, this quantity is always non-negative. Its integral is equal to 0. It means that it has to be 0 everywhere. Almost everywhere, phi of x plus phi star of y equals x scalar product y, which implies that Lebesgue almost everywhere y is equal to the gradient of phi of x. And that's the sketch of the proof. So as you see, it is mainly based on real convex analysis. This is in the case of Euclidean space. Now, what happens in a curved manifold? So, optimal transport in a curved space. And you ask yourself, take mu and u, two probability measures. On a Riemannian manifold, M, and consider the problem. Minimize, let's write it in the Monge form this way, integral of the distance from x to t of x square mu of dx under the constraint that the push forward of mu by t is equal to nu. What will it look like? It will look like t is the exponential of the gradient of something. The exponential, I recall the definition in the first lecture, I will recall it again. It's the exponential in the sense of Riemannian manifold, which means if I am here at a certain point, I want to go in a certain direction of a certain tangent vector. I go along this vector for time 1, and then I stop. So this is x, this is v. I send the geodesic in the direction v, and I look where I am at time t equal 1, and this here is exponential xv. So that's the definition of the exponential map. So for instance, in Rn, xv is just x plus v. I go in the direction v. And here, psi should have some convexity type property. Of course, when you are on a manifold, it doesn't have any sense. Convexity. What would it be, a convex function, if you are on a manifold? It could be geodesically convex, which means convex along geodesics. But here, it's a different notion. It's the following. And it's called d square over 2 convexity. It means that there is some function zeta from M to R such that psi of x is equal to the supremum of distance xy square divided by 2 with a minus sign, and here plus zeta of y. It looks weird, but it works. Notice here, if this is the Euclidean distance, and you expand the square, you will find here a scalar product of x and y, coming with a plus sign because of the minus here. And in fact, this will go back after some change of functions to the Legendre transform. So that, in fact, it is a variant of Legendre transform. This thing. This theorem is due to McCann and was proven around 1999. Was published around 1999. So what we see here, and that's the conclusion of this part, is that the solution of the optimal transport encodes some geometric feature. Inside there is a certain map. A priori, you know, we were looking for a full function, t, going from m to m. But in the end, we discover this function only depends on a function psi going from m to r. So there's a huge reduction of complexity. Instead of looking for a full function from m to m, we look for a real valued function. And this real valued function should have some convexity type property, so a strong geometric constraint, strong geometric nature. And so the solution of this optimal transport problem relies on a certain geometric properties of a function, a real valued function. Okay? So that's all we need to know for reminders about forage into the optimal transport. Optimal transport is a very developed theory. I wrote a few years ago a book on the theory, kind of comprehensive, maybe 1,000 pages thick. And if I wanted to rewrite it now, taking into account the developments of the 5 past years, the size should be double maybe. So, but this is all we will need here for the moment. And now, in the last 5 minutes, I will do further, just a further, no. Rather than going with the curvature, I will explain what they did, Jordan, Kinderlehrer, and Otto. And that will be, let's postpone all the discussion for curvature to the third lecture. So Jordan, Kinderlehrer, Otto, 1998, plus followers. So, on MG, Riemannian manifold, may be compact, or actually Ricci curvature bounded below. Bounded below by some constant, let's say minus k. Some constant which is real. Okay. Look at the gradient flow of h nu, with h nu of mu is plus integral of rho log rho d nu. So we will be minus the entropy. This is often called the Boltzmann H function. Information. So what did it mean? Look at this. So you will take, and taking nu of dx to be exponential minus v of x volume of dx. This is the Riemannian volume. It's the canonical notion of volume on your Riemannian manifold. Or Hausdorff measure. And this may be anything, any potential. So you have a measure mu0 is your starting measure, or rho0. And then you will have rho1, which will be defined as the minimizer of h nu of rho0 plus, plus what here? Plus the optimal cost C2 to go from mu0 to mu1. Let's put here mu0, sorry. Divided by 2 delta t. Where here, this is in terms of mu. This will rather put measures everywhere. Sorry for that. So I start with the measure mu0. And to have mu1, I take the minimizer of h nu of mu. This here is mu. I want the entropy to be as high as possible, so the information as low as possible. And here I take the minimum of the double integral of distance xy square pi of dx dy. That's why I put a 2 here, from mu0 to mu. And then mu2 to be the same minimizer h nu of mu plus C2 mu1 mu divided by 2 delta t, etc. I continue, and then I let delta t go to 0 with a mu k approximately mu of k delta t. Go to the limit, and it will converge to a solution of the heat equation. or Fokker-Planck equation if you take into account this potential V. So mu t will be equal to rho t nu, and d mu t dt will be equal to Laplace mu t plus divergence of mu t grad V. So it's a way to recover the heat or Fokker-Planck equation when you have the potential V as a gradient flow of the information, as the evolution which maximizes, in some sense, the entropy. So a very nice statistical interpretation, and it is nice to think that such an elementary and appealing way to see the heat equation was discovered so late as the end of the 20th century. That the heat equation is an evolution for the measures who want to maximize the entropy as much as possible. So, remark, a result of Ambrosio, Gili, and Savary show that it is still true with no smoothness in the context of LSV spaces. Even if you have zero smoothness, just having a synthetic notion of lower bound on the Ricci is enough to define a heat flow as gradient flow. And it converges to some object which has the right properties. And so it's even more general than manifold. Okay, my time is up for this second lecture. So here with this, we understood. So I developed, you remember, there were four blocks. Here there was curvature, optimal transport. Here there was entropy, and here there was gradient flow. And here we developed about the gradient flow and showed how we use this procedure with the entropy as a functional and the optimal transport as the measure of the distance. And we understood in which sense there is this link, which is the link of the heat equation. It was not clear where the convexity properties of the solution of the optimal transport play a role. But when we turn to the curvature, you will see that they play an important role. And this will be apparent in the third lecture. And that's it for now. Thank you. Yes, anyway, after lunch, it's normal that there is less questions than before lunch, because digestion takes a lot of energy.
Sorry, just reminding you that the coffee break, the coffee and tea will be served in third floor. There's 2 floors up.
Thank you.